this video, we will explore an alternative and simpler method to determine the rate law based on the initial rate determination. This method is particularly appropriate when your data is relatively straightforward and simple to interpret, as is the data in this table, and as will be the data that you will collect for Lab M. In fact, this data is the same data that we saw when we first of all explored the initial rate method approach to determining the rate law. But when we first explored this, we used a more mathematical approach, which involved writing out the rate laws for one experiment, the rate law for another experiment, dividing them, and mathematically determining the order with respect to each of the reactants. In this case, this approach is a more visual approach, it's a more conceptual approach, but actually underlines a little more specifically what the order of the reaction means with respect to each of the reactants. So let us get started. So first of all, we'll examine what happens with the oxygen gas. So if we want to determine the order of the reaction with respect to the oxygen gas, we're going to look for two experiments where the oxygen gas changes from one to the next and the nitrogen monoxide's concentration remains constant. So of course this is experiments 1 and 2. So it will be important that you indicate that that's what you're analyzing. So you're communicating your work by providing this kind of information. You will notice in comparing experiments 1 and 2 that the nitrogen monoxide's concentration stays constant. So it will be important to indicate that because of course if the concentration isn't constant, this analysis would actually not be valid. Next, we're going to look at what happens to the oxygen's concentration. It's easiest to go from experiment 2 up to experiment number 1. And so I can do this sort of notation. Looking from experiment 2 up to 1, I see that the concentration in fact doubles. So down here I can write the oxygen concentration goes up by a factor of 2. I then look at what happens to the initial rate. And if it's not obvious just by initial visual inspection, you can certainly plug these numbers into your calculator and see that indeed the rate, in this particular case, also doubles. So we say the concentration goes up by a factor of 2, and we also see that the rate goes up by a factor of 2. This means that the rate and the concentration are directly proportional. This, by definition, is what a first-order reaction is. In other words, a first-order reaction means that the rate and the concentration are directly proportional. So therefore, we can simply write, therefore, first order with respect to the oxygen gas. Next, we'll do the analysis of nitrogen monoxide. I'll change my pen color so we can more easily make that distinction. So we write nitrogen monoxide. So to analyze the nitrogen monoxide, we'll want to pick two experiments where the oxygen gas is held constant, yet the nitrogen monoxide's concentration in fact changes. So that will be experiments 1 and 3. So we'll write that down. We're comparing experiments 1 and 3. And in these experiments, the oxygen gas's concentration is constant. So we actually write that. Next, we inspect, well, what happens to the nitrogen monoxide's concentration? And clearly, its concentration will double. So we write here, nitrogen monoxide's concentration has gone up by a factor of 2. And then we inspect, well, what happens to the rate? And in this case, and I'll write it out here, in going from experiment 3 to experiment 1, the rate changes by a factor of 4. So I can indicate over here, rate goes up 4 times. By definition, this therefore indicates that the order of the reaction is not first order, but rather second order. So we can indicate therefore second order with respect to the nitrogen monoxide gas. This analysis actually works pretty well in the sense that for our particular course, we're only anticipating 0, first, or second order reactions. Therefore, it should be pretty clear what's happening when we do this kind of comparison. Now, if we need to write the rate law, we would say, well, rate is equal to K, and then the concentration of oxygen gas to the power of 1, and the concentration of nitrogen monoxide gas to the power of 2. I think you may agree with me that this sort of analysis is actually quite a bit quicker than having to write in all the concentrations and all the rate values and doing the subtraction. But again, you may only want to apply this approach when you have relatively straightforward set of data.